Alright, so for our next problem, we're going to be looking at a specific cubic equation of state. So this is the general form, and we're going to be looking at the SRK equation of state made by these three people, which has its own values of A, B, epsilon, and sigma. And I will be showing you how to code this into Python so that we can make a plot at many different temperatures, and you can see how the pressure and the volume relate to each other. So we're going to go to our Python window, and we need a line of code. So first thing we're going to do is we're going to come over here and we're going to copy this code, because this is a code that will give us access to some of the physical properties that we need. So we're going to use the git clone command, enter that in. All right, and then we're going to import or make this a library that we can use. So alright, so now we've imported this as something that we can import, so now we actually have to import it. So import tools.che as che, and then do that, and then we want to set up how we're going to actually call this as p is equal to che.props, because we're looking at the properties. And then for this example, we're going to use water as, our example compound that we're going to be making a plot for, but you could really use any equation or any compound that you want. All right, and then next we're going to need to import a few more things. So import numpy is np, and then from plotly sub plots import make subplots. So then on that. Okay, so that will just import stuff that we can use to make our subplots, or to make the plots that we're going to plot them on. So now we're going to need to define, the equations that we're using. But before we, that's the wrong thing. But before we do that, we're going to need, before we can define this equation and just plug things in, we're going to need to know what A is, we're going to need to know what B is, know what epsilon is, what sigma is. So let's define a function just for that. So we're going to define, we'll call it cubic ABES, so that's, A, B, epsilon, and sigma. And we want to input the temperature for this. All right, so we're going to need A equals something, B equals something, epsilon equals something, and sigma equals something. So over here, we'll be able to tell what these are. So first, let's go down to this table that has a lot of great values, and we're going to use, so we're using the SRK equation, so we come over here and look at that. Sigma is 1 and epsilon is 0, so that we can add that to the code. So sigma is 1, epsilon is 0. So now let's figure out what A and B are. So come back over here. So up here somewhere is the equation. Here's the equation for A. So A is equal to psi times alpha times r squared times critical temperature squared over the pressures, critical pressure. So let's type that in, and then we'll need to write an equation for psi and alpha, but let's just get this in there first. So it's going to be, so A is going to be equal to psi times alpha times, and then it was r squared. Okay, so we're going to need to define what r is outside of this. So add a line of code here where we just put that R is equal to 3.814. That might not be right. Hold up. Yes, constant. It's 8.314. I just remembered the numbers, but not the order. 8.314. Okay, so times the gas constant, and then times the critical temperature squared. So to get the critical temperature, we're going to need to do P dot TC. So that's going to give us the critical temperature. So that's just calling this function up here for the properties. And then we're going to want to square that. And then divide it by the critical pressure. So this is going to be very similar. So P dot PC. So that's critical pressure. All right. So now let's define psi. And we need to define alpha. So we'll come back over here and alright, so here's psi. So psi for the SRK equation is 0.42748. So we'll put that in there. So 0.42748. So 42748. 42748, okay. And then we need alpha. So alpha is here. And for the SRK, it says the alpha is equal to this expression. So let's type that in. So we've got parentheses 1 plus parentheses 0.48 right, and then plus 1.574 plus 1.574 times omega, and this omega we can get again from the properties, so times P dot W, that will give us omega, and then minus 0.176 omega squared, so minus 0.176 times P dot W squared, right, and then we have, alright, close parentheses, and then parentheses 1 minus TR to the 1/2, so we'll have 1 minus TR, so we're going to have to define TR. Let's put that in parentheses just to make sure. Right. This. And then all of that squared. So let's make sure parentheses match up. So that one goes to there, that one goes to there, goes to there. And your multiplication sign in there. Alright, looks good. So now we're going to need to define TR. So TR, and we can see from this document over here, here it is. Okay, so that TR is equal to the temperature divided by the critical temperature. So temperature divided by critical temperature we'll get from the library, and so that's how we get that. And now we need to work on B. So this is all for A. Now we need to work on B. So come over here, and for B, we have to find, okay, there it is. So B, we've got omega times R times critical temperature over critical pressure. So we'll need to define omega as well, but let's just write this all in first. So B is equal to omega times gas constant times critical temperature divided by critical pressure, I believe. Squared. These two are squared. Alright, so the next we're going to need to know what omega is. Omega we can get from this chart over here. So for SRK, omega is 0.08664. So 0.08664. Alright, so now we should have everything we need to solve for A, B, E, and S. So we can return those values. So return A, B, E, and S. Alright, shift enter. Alright, so it appears to have worked so far. Or at least that there's no glaring typos there. So, next thing we're going to want to do, now that we have this, is actually define, the equation itself. So, how are we going to calculate these pressures? So, we're going to define, and we'll call this one cubic underscore P for the pressure. And this one, we're going to need to input the specific volume and the temperature. Alright, so then we're going to need to call the ABS values that we wrote a function for up here. So A, B, E, S is equal to cubic ABES of temperature. Right? And then we can return, we're going to want to return the calculation for the pressure. So here we can actually, let's just return pressure, and then we can find the pressure here. So pressure is equal to gas constant times temperature over specific volume minus B. So got gas constant times the temperature divided by specific volume times, or minus B, right? And then minus A over specific volume times specific, minus A times specific volume plus epsilon B over A and divided by, and then it was specific volume plus epsilon times B, so specific volume plus epsilon times B, and then times specific volume plus sigma plus B, so specific volume plus sigma plus sigma times B. Alright. And then make sure all our parentheses line up, so we've got those ones. Yes. Yep. Alright, I think we're good. Alright, so I recorded the last part of this, or the first part of this video pretty late last night, and I made a couple of typos throughout this, throughout these equations, so I'm just going to go through and show you where those were, and fix them so that we can continue on with the rest of this code. So the first one is looking at this A and this B. You'll see in the B I have the R squared and the critical temperature squared, and then the A I don't, whereas in reality those should be flipped. So the B does not have any squares in it, but the A does have the squares. So I think I just looked at the wrong equation when I was doing those, got them confused somehow. So I'm going to fix that. So for A, R should be squared, and the critical temperature should be squared. But for B, nothing should be squared. Alright, and then the next error that I made was when calculating the pressure. So you'll see over here that there are two terms separated by a minus sign. In my code, I have the two terms separated by a division sign, so that should be a negative. Alright, and then we can just go ahead and reevaluate everything and make sure that those errors don't affect any future code that we make. Alright, so next we can go ahead and start plotting this. So we're going to need what we want to plot. We're going to make a pressure versus volume plot, so we're going to need to, find volumes. So we can just plot, let's start with like a linearly spaced amount of values for our V, and then we'll calculate P using this cubic P function that we made. So for V, let's start with np dot min space. Alright, so I guess how low do we want to go? So if we think about this, our volume can't be 0, because zero volume doesn't really make any sense. And our volume really shouldn't be greater than the excluded volume, because that also wouldn't make very much sense. So how about we make our lower value like 1% bigger than B? So we can do that by going 1.01 times B for our first value, but that means that we're going to need to define B. Because we've defined B up here, but we haven't called the function yet, so the code's not going to know what B is. So we can do that just kind of by copying this code up here and just pasting it down here. And then, copy the omega, just stick it in the omega spot. Alright, so now I'll calculate B for us and then use that to calculate our V values. So then we'll want to go up to quite a bit bigger than the excluded volume, because the excluded volume is the volume of molecules in the gas, and their molecules are not very big, so we're going to want quite a bit larger than that. So let's go like 1 times 10 to the 6th times B, and then let's say we want 500 points. Alright, so we can start with that. So then we're going to need to define our pressures. So we can use the cubic pressure function that we made. So let's call that. And we need to import the volumes. And we have those, so it'll import all the values from up here. And then we'll also need to import a temperature, or input a temperature. So let's make a temperature. So for now, let's just choose a random temperature, say 400 Kelvin. And I'll show you how we can do it for a bunch of different temperatures here in a second, but we want to make sure that our graph looks good before we go about and do it for, a bunch of different values. Alright, so now we want to make the subplots. So fig equals make subplots. And then, alright, fig dot add scatter. Alright, so for our scatter, we're going to want our x's to be our volumes. We're going to want our y's to be pressures. And then let's make our mode markers to start. Alright, so let's shift enter and see what this looks like. Alright, so you can see here we've got something interesting going on here, but it's kind of hard to tell what, because there's not really a lot of points in between here and that value that was all the way up here. So one way we could maybe fix that is maybe by doing like a logarithmic scale. So let's try that. So fig dot update x-axis, and that will be type is equal to log. So let's shift enter there. All right, so that looks better. You know, you can tell scale-wise on this graph, but we still don't have any points in between here. That's because we're going to need to. That's because our values are lin-spaced. So they're linearly spaced, but they're on a logarithmic plot. So we're going to need to logarithmically space these values. So we can do that using the log space function instead of lin space. So the difference between log space and lin space. So for lin space, you put, you know, the first value that you want it to start at, the last value that you want it to end at, and then how many points. Log space is similar, but you actually put like the power that you want it to start at and the power that you want it to end at. So let's just take the logarithm of this value and it'll give us, you know, the power of that. So because then it'll just be the power of 1% bigger than b. We can do the same thing for the larger value. Just take the log of it. Right. Shift enter on there. Okay, so now you can see we've got something more interesting happening down here. Let's zoom in so you can see it a little better. So you can see that the graph kind of goes down, and then it kind of goes back up, and then I've kind of cut it off, but it goes down again, you know, over here. Alright, so the next thing that we're going to want to work on is making these plots for multiple different types of temperatures. We don't want just the temperature at 400, we're going to want a range of temperatures. So we can do that with a for loop. So for temperature in range. Alright, so then what should we have our lowest value be? Maybe melting point of water. And then we can go up pretty high, so say 800 Kelvin. And then let's say we want to graph 25 temperatures. Alright, we'll see how that goes. Alright, so now we want to figure out what we want inside of our for loop. So we have the temperatures looping. We're going to want the pressures to loop. The pressure calculations to loop because those depend on temperature. We're not going to want the subplots to loop because we don't want a new subplot for every temperature range. So we're just going to cut that from there and then stick it outside of the for loop. We will want a new scatter to be added each time, so we can put that inside the for loop. Alright, and then we don't need to update the y or the x-axis each time, so we can just leave that outside. Yeah, so let's plot that, see how it looks. Alright, you can see we've got quite a lot going on here, but it's kind of squished down here. So let's maybe, so we probably don't actually need to go out quite as far in our V's. So maybe instead of like 10 to the 6th, about, we can take that down to like 10 to the 4th. So we can try that. Still going out pretty far. Let's decrease it a little bit farther. So 10 squared. We can decrease it even farther. I don't know, maybe -2. That's looking a little better. We'll leave it there for now. And then another thing, kind of these dots all kind of get a little bit confusing. So instead of markers, let's have them be lines. All right. And then, okay. So then you can see it's labeled each of these, but like we don't know what trace 17 means. Like, so we're probably going to want to label each of these plots, and we can do that by naming them. Or we can use an F string. So for an F string, we can set the temperature equal to the temperature that's currently iterating, and then we can say the units are going to be Kelvin. Simply shift enter on that. You can see that now these are labeled the blue ones, 273 Kelvin. so on. So that's a lot easier. We probably still want to scale this a little bit. Let's try scaling the y-axis a little bit. So big dot update y-axis and range. Let's say maybe from negative 200 times 10 to the 6th to about 200 times 10 to the 6th. Let's see what that looks like. Oh, maybe I put some new parentheses on here. Oh, no, I know what I did. I forgot the equal sign. There we go. Okay, so you can see that range looks, quite a bit better. We can see all the variation in this part here. And so that's how we're going to graph our generic cubic expression of state. The SRK version for a whole bunch of different temperatures. You could do similar things for the other cubic expressions of state. You just have to use the specific formulas for those specific numbers. But yeah, so there's our plot.